Hello, and welcome to another session on data mining. Today we're going to talk about different types of neural networks. Now, we've seen that deep learning libraries allow a very abstract way or a very easy way of representing different types of neural networks, and that has given rise to a very large variety of neural network architectures. We have discussed two different types of architectures so far. One of them was the fully connected perceptron or the feed-forward perceptron, in which you feed an example in all the features of that example which are passed on to all the neurons in the next layer, which are connected to all the neurons in the next layer, and so on. So there's dense connectivity across different layers of networks. We saw that that can be problematic when we are dealing with data such as images, in which case we talked about convolutional neural networks and how they are able to model different invariants and structures within the data to learn a more or a richer representation with fewer parameters because they enforce locality and shared weights. So we talked about these convolutional neural networks, which use a different type of architecture in comparison to these multi-layer perceptrons, but that's not the end of it. There are other types of neural networks such as residual networks, recurrent networks, autoencoders, adversarial networks, graph networks. If you can dream it, you can essentially build a neural network out of it. The point is that it should be useful. Everything you see on your screen right now presents a significant step forward in the development of neural networks or deep learning. So we started off with very simple neural networks with fully connected ones, multi-layer perceptron ones. Then we moved on to more convolutional neural networks. That was a huge step forward. At the same time, people were busy trying to model in history. People were busy trying to model different type of time series, and that gave rise to recurrent neural networks. People have been able to build deeper versions of neural networks, which are called residual networks. Now, what people identified is that once you have a bunch of convolution layers or a bunch of fully connected layers, there's only so much you can do before you run into optimization failures. And that led to the development of these residual networks. At the same time, people were trying to compress information, just like PCA allows you to compress information based on the associations between different types of features of an example. These autoencoder networks are information compressors that you can feed an example in, and a reduced representation of that information or that example is built that allows you to reconstruct the whole of the example. But this is done using neural networks, and these type of neural networks are called autoencoders. So they encode the input representation that they take in, and then they're able to reproduce that, much like PCA, that particular example. A major step forward in terms of neural networks was adversarial training, which is game theoretic training of neural networks. It's an excellent idea, presented a huge step forward for neural networks, and we're going to talk about that. Now, graph neural networks are another cool way of representing different types of data. So images can be viewed as graphs, but there is so much other type of data that we can. So for example, social network data is not an image, and if we want to apply neural networks on top of those or to identify, let's say, communities in a network, these neural networks can be used for that purpose. And they generalize the notion of convolution from images to convolution over graphs. So that's another huge step forward in the development of neural networks. So people have tried to develop different types of neural networks, and some of those architectures can be seen on this particular slide. You can have very simple feed-forward neural networks. If you use specialized basis functions or activation functions called radial basis functions, you end up with very interesting type of neural network called radial basis networks, which are very good for classification problems. You can have deep feed forward networks in which you can have multiple layers. If you want to model time series, you can use these recurrent neural networks, which have connectivities onto themselves. So each neuron can essentially give feedback to itself about its internal representation or its output, and that allows us to model different types of time series. And we're going to talk about them in a bit more detail later on, but that is essentially the idea. Now, once we have, let's say we've got PyTorch or another deep learning library, all we need to do is to implement the forward representation. So take an example, how does the neural network generate its output? If we can implement that, the rest is taken care of, right? So that's essentially why we have so many architectures now. With the development of these deep learning libraries, it has become really easy to develop novel architectures and to solve different types of machine learning problems. So we have these autoencoders as well, which, as I said earlier, allow when you feed in an example, it learns a lower dimensional representation of that is able to reproduce that particular example. So it's a really useful idea for information compression. Now there are different types of variants. There are different variants of it that allow us to not only model or compress the information contained in a given example, but also we can create different variants of the same example. So let's say if you take a picture of a person from this angle, we can use a variation autoencoder to essentially generate a picture of that particular person at a slightly different angle. So that is where these are used. You can have denoising autoencoders. There are sparse autoencoders available. We're going to talk about them in a bit more detail later on. But I just want to give a very high level overview of how different type of neural network architectures are possible. And you can have other type of generative learning models such as a Markov chain, a Hopfield network, a Boltzmann machine, a restricted Boltzmann machine, and a deep belief network. There can be a whole module dedicated to these, but what we are doing over here is trying to create examples or generate examples. And we can have deep convolution networks, we can have different variants of that. We can have adversarial training in something called GANs, which are pretty popular these days. You can have residual networks. Support vector machines are also a special case of these neural networks with kernel support, and there is a growing body of knowledge that is trying to exploit the good things about support vector machines, that is their theoretical foundations, and port them over to neural networks and identify different connections between neural networks and kernel machines. So this is a very interesting area of research as well. There are specialized language models and such as neural Turing machines, and it's essentially the possibilities are endless. However, we are going to start simple. We've covered two types of neural networks, those being convolution neural networks and fully connected ones. And we are going to next talk about residual neural networks. And before moving on to those networks, though, it is really important to understand why we needed them. So if you are trying to solve a complex machine learning problem, and you have about 5 layers, and you train your neural networks well, you initialize your weights properly, you have got a good optimization method, and you have enough data, you should be able to learn for up to 5 layers. If you have more than 10 layers, you probably want to initialize your neural networks more carefully, and you may want to use Bayes normalization for it to be able to converge. However, what people saw is that they weren't able to develop deeper networks because of optimization failures. Remember, the deeper you go into a network, the more problem you have with exploding and vanishing gradients and other type of optimization failures, especially due to the number of parameters and their associations or their impacts on one another. So people started trying out all types of tricks back in around 2006 to 2016. That decade, people were trying all sorts of tricks on how you can go deeper or make deeper networks by doing better weight initialization, better Bayes normalization, but what really solved the problem was a very simple idea called residual networks that we're going to discuss next. These networks use something called skip connections. It's a really simple idea, and I'm going to talk about that, but it has been used to develop really deep networks of up to about 100 layers or so, and even networks deeper than that are now possible. So let's look at this idea of what happened. So when people were trying to increase the number of layers in a neural network, let's say they were trying to solve the CFAR classification problem, which is a 10-class classification problem, and they use a 20-layer network or a 56-layer network, they noticed that the training error and the test error of a shallower network was actually better, or it showed better convergence during training, and it showed better generalization on testing in comparison to deeper networks. And that was really surprising, and people saw what's going on. And then they identified that simply stacking layers doesn't essentially solve the problem of learning because of optimization failures. So overly deep plane networks that are connected, like you have multiple layers and they're essentially deep, there are multiple layers of those, you can end up with having very high training errors. And that led people to identify the issues that were there in terms of optimization failure. And they noticed that as you go deeper into or as you add layers for solving this problem, your training error also increases. So although the capacity or the ability of the network to memorize all the data should increase with the increase in layers, but that's not what they saw. They actually a deeper network was worse off at generating or learning the training data set in comparison to other ones or to shallower networks. So uh, they identified that problem, and the reason was optimization failure. So in a plain network, what happens is once you have a given input, it passes through a wait layer, an activation function acts on it, and that output is passed on to the next one, and then you have an output which is compared to a target, and then you can have and then you can optimize over it. Okay, so h of x, let's say, is somewhere in that deep network that we are trying to create, but it's a plain network in that it's essentially a feed forward network in which there's connections between different layers and like this one. So let's say we're trying to learn this representation that allows us to solve a given classification or another machine learning problem. Then what we are doing is we are trying to update these weights, all of these weights that you see over here, and we want our output representation in a way that it is able to solve that particular classification problem. So h of x is our desired mapping, and we hope that the two weight layers here fit that particular internal representation of that example that then allows us to solve that particular problem. But if we have enough neurons in our or enough layers in our neural network, we can run into vanishing and exploding gradient problems, which can be overcome to a certain extent by adding by adding Bayes normalization and by doing dropouts, but that still doesn't allow me to go much deeper. And then they came up with this idea. This was published in CVPR 2016, and the idea is called residual networks. And what they did is it's a very simple and elegant idea. What you do is you pass the input representation x through some skip connections to the output layer of your of this block that you see, block of the network that you see. Now, if you represent this as is shown on your screen, if you want to learn, I apologize, sorry, if you want to learn your representation over here, which is h of x, now what you've done is essentially broken up the problem. We already know x, right? And all we want to learn is this f of x bit, which is the difference between the representation that we want to learn and x. So adding these skip connections, as they're called, allows you to reduce the problem. So essentially each layer is learning only the part of the representation that the previous layer has not been able to figure out. So that is why each of the layers, or if you view them in multiple layers, each of those blocks is essentially learning a residual error or a residual of the representation that the previous layers have not been able to learn, and that simplifies and localizes the problem. And you can now use this idea to train really deep networks, and that's what they did. You can build essentially very deep networks. So this is a pictorial comparison between a plain network and a residual network, or ResNet as it is called. So you have your input representation image going in over here, and then you pass it through all of these, and then you get an output. In this case, we're trying to solve a 1000 class classification problem over the ImageNet or the CFAR dataset. And this is what the architecture of a plain net would look like. You would have multiple convolution blocks, each one of them passing on to their outputs onto a final classification classification block. So all of these are learning features, just like we have talked about. So this is a deep convolution network. Okay, so this plain network is a deep convolution network. Each of these layers can be expected to learn a representation that is relevant to the problem that you have. However, this, because it's so deep, we may end up with optimization failure because of vanishing and exploding gradients. You can use Bayes normalization and data augmentation to circumvent that problem to a certain extent, but what they saw is that this actually is it still doesn't solve the problem completely. However, if you add skip connections in the following way, so you have an representation built over here. So if you think about each layer in a neural network, you pass your input example in, it does some processing on it and generates an output, right? So that is what I mean by representation over here. Now that representation is of course passed on to the next block. So this is what I mean by a block. You have in the same block you have two convolution layers. Each of that representation is received over here, and then it is passed on directly as well to this network. So now these two layers in over here are going to learn the residual of the representation that has not been learned up till this point. Okay, and it's going to try to do that, and then the next layers. So this is a recurring structure sort of. So the next block is then going to learn the residual of that representation and so on. So this is going to have a more. It's going to have a more is going to have more flexibility or more localized residual learning in comparison to an original network, so it would be more efficient. And because your gradients now have a shallower path going backwards, right? So they don't have to go through every layer. They can also skip back through each alternate or after two layers. You're not going to end up with that much of an issue in terms of back propagation or exploding and vanishing gradients as well. And what they found is that we're going to come to the implementation in just a bit. What they found is that if you use a plane network, then what we see is that you have different layers, and shallower networks are actually better in trying to minimize this error or training error in comparison to deeper networks. Okay, and the same thing holds in both train and test. Okay, so this is the training error. The dashed ones show the training errors, and the solid lines show the test errors. So as you can see that deeper networks have actually higher errors in both training and testing in comparison to deep networks if you don't use these skip connections for this particular problem, which is a 10 class image classification problem. Okay. However, if you do use these skip connections, what you end up with is that deeper networks are actually able to do better than shallower models, and they're able to do better than the shallow models used in the plane network. So deeper ResNets actually generalize better, and they're able to give lower training errors. So they have a higher capacity, are easier to optimize because they're only learning the residuals, not the whole of the representation at once. So they are able to generalize better to these unseen cases. So not only on the CFAR dataset, but also on the ImageNet classification problem, deeper networks such as the 34-layer network, which is popularly called ResNet 34, and then you have an 18-layer block, which is called ResNet 18. So this is able to do better in comparison to these planar networks with the same number of layers. Okay, so deeper networks over here have lower training errors, which means that they're able to memorize everything. Okay, and if you stop them at the appropriate time, you can actually get lower test errors as well in comparison to shallower networks. So what this essentially proves is that these residual networks, because of their ability to learn residual hierarchical representations of your data, they're able to do better. Okay, and these has been shown in terms of your of a number of data sets over here. So this model has, so they're not as complex, and deeper ResNets are actually they give you lower errors, and there have been really people have developed really deep types of residual networks, even up to 1,000 layers. I've read somewhere, and these can offer really good prediction accuracy. So over the years, the neural networks have gotten deeper, and their prediction performance has actually, or generalization performance has significantly improved. So this network, which was a shallow network, ILSVRC in 2010, was a shallow network. It gave an error of 28.2% on ImageNet classification. And as we increase the depth of the neural network, which is shown by this orange line over here, we see that this network in 2015, this network ILSVR15, which is a ResNet, is able to generate a prediction error of 3.6% about, which is much lower than the human generalization performance on this particular data set. So there's some criticism on that as well, but this is a good demonstration point in that deep res nets are actually able to do better in comparison to deeper models without these skip connections. So it's essentially the idea of skip connections that allows you to learn better, and it has won multiple. These skip connection networks have won multiple different challenges in on image classification, segmentation, and detection, and so on. And it's significantly better than its deep or shallower counterparts or counterparts without these skip connections. If you want to read more on this, I would strongly recommend you read the original paper. It's a really simple paper. The idea is really simple. What you essentially do is pass on the representation that you have. You just skip that onto the next bit so that these two layers in the middle now essentially learn the residual of what your actual representation should be. There are many third-party implementations available. You can use them in transfer learning if you want to do that for your assignment. Let's say you can use that this link over here, but I strongly recommend that you read this paper. And now let's come back to the implementation in PyTorch. Now we're not going to implement a whole ResNet like this big beast that we saw over here. Okay, what we are going to do is to implement a single block where we have a single connection. Okay, so this is how it looks like. What we pass on is you have a bunch of inputs and you have a bunch of outputs. You specify how many inputs and how many outputs you want, and then what you do is you simply pass your network or your representation through your weight layers. You apply an activation function on top of that, you pass it through another layer, and then what you do is you add your output, your residual, which is this bit. Okay. So this is learning the residual, which we call f of x, and we add it to x. So this is where this skip connection is actually taking place in terms of the actual coding. Okay. Now this is a very high level overview of how you can implement these residual networks in PyTorch. If you want to take a deeper look at this, is a strongly recommended resource for that. Please go and take a look at that. The authors explain how you can build a deep residual network with these skip connections from the bottom up. So if you're new into this area, I would strongly recommend that you take a look at those transfer learning resources, and once you have a good idea of that, you can move on into learning about these how it's done at a more deeper level using this resource. So I hope you have grasped the basic idea of residual networks and how residual networks are able to learn better because they're just learning the residual of the representation. So this idea of residual networks has led to other significant steps forward in neural networks, including the modeling of neural ordinary differential equations. So it's important that you understand what went here, okay, and how these ResNets work, because these skip connections are used in a whole bunch of other types of neural networks that are used for image segmentation, for detection, for solving differential equations with neural networks. So this is a crucial conceptual point. Okay, thank you.